Alright, so we're looking at question 9 of the photoelectric effect optical phenomena worksheet, and we're now looking at a question that was taken from the Department of Education's November 2011 paper. So they tell me a metal surface is illuminated. Now the word illuminated here simply means that light is shone on it, okay? And they tell you that it's got a wavelength of 300 nanometers. Now remember, we can't work in nanometers, so that's 330 times 10 to the minus 9. We're going to do that straight away. This is a very usual conversion. Okay, then they say to us the minimum amount of energy required to eject an electron from the surface of the metal is 3,5 times 10 to the minus 19 joules. Now they've underlined a whole bunch of information. If something is underlined, bold, italic, or in capital letters, they want it to stand out. So they're telling you it's important, okay? And the picture they give you shows you the ultraviolet light hitting the metal and then electrons coming off. First thing they say is name the phenomenon illustrated above. Well, we've done enough of these now, so we know that's the photoelectric effect. Then they ask us, give one word or term for the underlined sentence in the above paragraph. This is just another way for me to ask you a definition. Instead of asking to write out the definition, I've given you the definition. And that definition was the minimum amount of energy required to emit an electron from the surface of a metal. That's the work function. It's just another way around of asking it. Okay, work function. Then they want the frequency of the ultraviolet light. Now they've told you that the wavelength was 330 times 10 to the minus 9 meters. We want frequency. We remember that C is F lambda, C being 3 times 10 to the 8. We want the frequency. This is 330 times 10 to the minus 9. So my frequency, I divide both sides by 330 times 10 to the minus 9, and we get 9,09 times 10 to the 14 hertz. Okay. Calculate the kinetic energy, so EK, of a photon emitted from the surface of the metal when the ultraviolet light shines on it. So we look at this and we go, well, I've been given WO. Okay. I know both wavelength and frequency, and we want EK. As soon as we're looking for EK, we know we're going to use this equation. Okay. Now, we don't have E, so we know we're going to have to use HF. WO was given to me, and I want EK max. So HF is 6,63 times 10 to the minus 34 times by the frequency we just worked out. Ooh, and that's 14, not minus 14. Let's write that so you can see it. We know that this is 3,5 times 10 to the minus 19. And we're going to add it to EK max. Of course, you're going to multiply that together, and then you're going to minus the 3,5 times 10 to the minus 19. And your max becomes, if you just put it as EK, it's fine, 2,53 times 10 to the minus 19 joules. Okay? It's a small amount. It's what I expect. Then, the intensity, brightness of the ultraviolet light illuminated the metal is now increased. What effect will this change have on the following? The first one is kinetic energy, and all they want you to write down is increase, decrease, remains the same. When we increase the intensity, we do not change the kinetic energy of the photons, which means we can't change the kinetic energy of the electrons. So this one remains the same. Then they asked us the number of photoelectrons emitted per second. Well, by increasing the intensity, we are increasing the number of photons that are being put onto the metal. And if we increase the number of electrons, we'll increase the current. So this increases. Okay, not so